C++ or C or something like that? Do you think so? Does it understand that? No, it doesn't. It understands only one thing, the binary code. Yeah, so it understands only zeros and nulls. Of course, put in the right direction, in the right order, and in the right size, to make them possible to create some package of information which we call words. Yeah? So word is a packaging of the information which we are working on. And this word can have different size. It depends on the system. In our example, this package would be for Intel 8051 families. It would be 1 byte, so it would be 8 bits. And what you can see is the very short scrap of the instruction table, which has about 60, 70 instructions. It depends on the processor, on the microprocessor. And in this scrap, I'd like to explain you how does it work. And we started with that the first column with the name instruction is the column which we can put directly to the microprocessor. And we can say that way that the microprocessor has the same table as we have. Unfortunately, microprocessor doesn't use PDF format or any other formats like that, so it can't read the forms of in that form as we can read that, but it can understand, because it is constructed this way, that if microprocessor gets such an instruction, it understands that it should now add something from register, which is called B in this example, to the register which is called accumulator in this example. And it's enough. It's enough to operate it. So, why we have another columns in this table? We have this hexadecimal description. Why? Because it's the easiest way to read 1 byte. Why? Because all 4 bits can be written in one hexadecimal number, right? Every 4 bits can be written in one hexadecimal number. So 2 hexadecimal numbers, digits, yeah, can be 1 byte, and each byte we can we can write in 2 hexadecimal numbers. Of course, when we develop some software in assembler, in this very basic software for every microprocessor, we have to do it somehow. It would be very strange and very difficult for us if we are forced to write this code that way. So if we have to write only ones and nulls and zeros, it could be like that, because the processor understands it, and all the every instruction has its binary code, but it would be very hard to understand for us, for people, yeah, because we are rather familiar with symbols, for some mnemonics, yeah, for some abbreviations, and so on. That's why the first step of understanding it and of translating it are the assembler environments, which translate this binary code which processor understands to the mnemonics. So to the short comments which we can write in our assembler in our assembler emulator. Of course, we have also the description what that instruction does, because we want to know if such instruction is in memory and or in our code is such a mnemonic, what's going on. Yeah? We know that it adds the register B to register which is called accumulator, and the result is in accumulator. Okay. So now we know and we are conscious that processor understands only binary code, yeah? And this mnemonics, which we call assembler, is only a mask. It's only a language more understandable for us, which we can use programming in assembly. Okay, and this slide is to sum up this what we're talking about. That machine instruction represented in mnemonics, and it's only the representation of that, and it's the one-to-one correspondence. So one mnemonic has only one code, or maybe on the other hand, each mnemonic can be translated only to one code. If it's completely the same. Yeah? Why are we going back to the assembler? Sometimes it's necessary, and all the programming environments which you are familiar with or which you will be familiar with allow us to implement some scraps of assembler code into our high language codes. So we can put into our C++ code some fields in assembler to operate on some lower operation if it's required in some specific situation. Okay, so maybe have a short break because it's 4 minutes. And we'll finish it. Okay, have you ever tried programming any microcontroller in assembler, or it's completely strange for you? It is, yeah. So I'd like to show you that I'm not kidding you. It's true. It's an Intel 8051 microprocessor family emulator. And only a short example, yeah, that we have it all like that. For example, I can put the instruction mode, which is the instruction to move some data. For example, from the code to the register, which is called accumulator, yeah? So I'm using now this instruction, to move some number from code to accumulator. and just to show you, we've got here the view of two types of memory. We're talking about memory. Yeah, we've got, of course, we've got a lot of types of memory, but the simplest, we can divide it into data memory and program memory, and we're forgetting now about it, how it is realized, yes, how it is implemented. Yeah, we are talking only about program memory and data memory, and we know only that in program memory we've got our software, and data memory we use to save and keep our data. So we can see the data memory and program memory or code memory. So in code memory, we've got the code we've just written, and the code is about moving some data to accumulator, and we can see that we've got 2 bytes here in the memory. So we can compare it to the list of instructions, and in the list of instructions we can see that this instruction which we are talking about, code, is 74, and exactly the same code we can see here in our code memories. What's next? The instruction was what was the instruction about? About moving some data from this code to some other place, yeah? And this data was in this code. So the data should be in this code, and it actually is, because the data was number 5, and this number 5 is in our code. So I proved that what we write here in this mnemonics, using this assembler mnemonics, goes to the microprocessor through the code memory as a code, not as a symbols and mnemonics. Okay? Going deeper, because we've got here some 74. What 74 means for microprocessor, it means nothing. But in every computer you can find another magician device, magician instrument, and this instrument is calculator. And listen to me now, because your embedded calculator, which is in each of your Microsoft Windows system, has a great option which you can find here. It's in Polish, I'm sorry, but in English or in Romanian or Moldovan? Romanian, yeah. It should sound similar. So you can find the programmer's version of this calculator, and you can very simply calculate and recalculate the hexadecimal, decimal numbers to binary numbers. It's very useful, and I recommend it for my students at the beginning. And I don't want to teach you now how to do that, but if you have some classes about programming or microcontrollers or so on, I recommend it to you to show this sophisticated device to your student at the beginning, because it's in every Microsoft Windows system, and it's really, really useful when you are taking into account programming this lower layer of programming. Okay. So, one more thing which I'd like to show to you. So, do you remember what this instruction was about? I told you what is going on in the next step. What will be the effect, the result of this instruction? This data, this number 5, will be moved to this register. And this register is another kind of magic, another piece of magic. It's something A. What does it mean? Well, we know already that it means accumulator, but I said a few slides before that these registers, so also the accumulator, the register B, and so on, it's not somewhere there in the sky, but it's also in our memory. So let's do that. Let's do this step. And after this step, we are looking inside the data memory, and then we can see that we've got nothing, because accumulator is a register stick into the processor, so we have data there. But if we want to move some data into another register, one of these 8 special registers from R0 to R7, so for example, let's move to the register 0, the data which is in accumulator now. And then we can see that this data appears in one of the memory cells. So it means that this register, the map of these registers, is in our data memory. So another thing which I was talking about in my presentation. Okay, let's move back to the presentation then. So, we've got this lowest part of programming with assembler, which is directly translated to binary code, which microcontrollers understand. Then we have high-level languages, and these are languages which you are more common with, am I right? So we have Basic, C, C++, C#, Java, and so on. So, these languages are mostly depend on the software which is on the device which we are going to develop software for. So, if we are working on some computer with operating system, we develop our software actually not for the specific processor or specific microcontroller which is inside, but we develop software for the operating system, and it doesn't. We don't have to be aware what is inside. We only have to know on which operating system we have to work. What is the what are the advantages? Of course, it's much easier for us to translate so-called business logic. So it means that someone, for example, from your CAE comes to you and say, you do for me the software which controls the airspace around us, and poor software developer sits and, what am I going to do? I don't understand anything. What is he going to do? What is he going to want for me to do? And sometimes it's hard to translate this business language, this language about your needs, language about your requirements, to the software. And these high-level languages, especially Java and C#, facilitate it, because there you can create in the software the business parts, which are parallel to the requirements which you got from somewhere. And you don't have to really understand what is going on deeper, what's going on underlying. Because sometimes another objects from another libraries which you got from somewhere do it for you. And this is the main advantage of high-level languages. What is the main disadvantage? That you don't have full control. Yeah? The easier way of programming, the easier way of translating the business logic to the software, the lower, the less control you have. And it has always been, and I think that it's not possible to change it. But, as I said, you have an opportunity and a possibility to put some scraps of low-level code to high-level language software. And it's possible as well in C, C++, and also in C# and Java, which, as you know, work not only on operating system, but also at additional framework. Yeah? For C# it's .NET framework, for Java it's Java framework. So on the operating system, you've got another entity, another something which works on your operating system, and on this works your software. So there are a lot of pieces of code between you and your software and between hardware, whatever it is. Okay. So when we're talking about a microprocessor-based system, what can we have here? We've got, of course, this microprocessor unit with some inputs. Yeah, it was on the previous slide, so you're familiar with this. On the other side, we've got memory and some outputs. But to that inputs, what can we connect to that inputs? For example, we can connect to the input analog decimal converter. Then we can connect some sensor. For example, in this example, it's a temperature sensor. So what temperature sensor does, you know, yeah? It measures the temperature. And this temperature is translated to the analog voltage change. So the higher temperature, the higher voltage, for example. Yeah? And then this analog voltage signal goes to the analog converter, and then we can convert it to decimal signal and put it to our system in the digits. So no more analog voltage signal, only digits, which are the signals read in some pieces of time. What can be another sample of device? For example, timer, which gives us interrupts in some time, for example, some periods. To the output, it can be some fan or some heater and whatever you can imagine. Important is to remember that we can put not only one device into this bus, but we can do some structure with devices where at the end is some sensor and at the other end is some input to our microprocessor system. What about microcontroller-based system? In microcontroller-based system, all these parts of the system, so microprocessor, memory, inputs, outputs, and some support devices are integrated in a single chip. So you can't integrate in this system after delivering. So you can integrate into it if you are a microcontroller producer, manufacturer. You can design this microcontroller as you want, but you are not, I'm not. So we can only, what can we do is buy microcontroller, and when we buy this microcontroller, we can't change anything inside, unless it's FPGA, but it's another story. Yeah. So. What's the main sum up of this? What's the conclusion of this thing? That we don't have any possibility to get into buses. So we can't integrate into data buses, address buses, and this control bus, which I was talking about. What about input-output ports? They can be generally multiplex and can be programmed that way that you can use one input-output port or pin to many devices. The good example is in this 8051 processor, microcontroller, this one, chart. That, for example, to port 1, you've got connected LED here, but as well, you've got connected the display, the 7-segment display. Yeah, it's only one port, but it's it can be chosen by multiplexer which device is to be used in the particular operation. So you have a number of inputs, outputs, but you can use it for many more devices. So what's the structure of a microcontroller-based system? It's similar, but we only have to remember that all these parts of the system are integrated, and we can go inside. Let's move to Arduino board, because as I said, it's the simplest way to start with programming microcontrollers. That's why we decided to start with Arduino. That's why you bought Arduino, and we are going to try to prepare some software to remove some elements and power some LED, for example, during our practical workshops and days. So, what the Arduino board contains? Of course, there is a microcontroller unit, and in this way, in this example, it's Atmel Atmega 328. But in a circuit board, there are also a lot of other devices which we can use without connecting anything else to the board. What is it? So, it's LED, which you can bring, for example. It's a button, press a button, which we can reset our system without any other signal from outside. There's another LED, and transmit receiver LED. We've got a universal serial bus port. And of course, we've got a lot of peripherals, inputs, output pins, which we can connect to. A few words about the microcontroller, which controls the Arduino board. It's 8-bit AVR microcontroller in this architecture. With such parameter, I think that it's not so important for you now to scrutinize it. Is it? Or isn't it? You can find it on the internet, so it's not very secret information. I'd like to underline only the fact that we've got analog decimal converter on board, and we've got PWM generator with 6 outputs there. So we don't have to connect any other device to generate the PWM signals or to convert analog signal to decimal, which we're going to do. And of course, we've got timers, counters, which we can use in our operations. A few words about the beginning, what the Arduino is. When we are talking about Arduino, we can't say it's a microcontroller because it's a philosophy, yeah? It's a movement which was started with these two guys. And the main message from the guys was to make it simple, yeah? Make programming microcontrollers as simple as possible. And they developed some open source philosophy, how to do it, to make it simple. And as you are in this business, as you are programming microcontrollers, Arduino microcontrollers, you know that the realization of that Arduino philosophy are on different chips in different configurations. The first, the simplest are with AVR, the more sophisticated are with STM32. For example, our micropilot is also with STM32 microprocessor, microcontroller. So we can't say that Arduino is composed of some elements. Yeah, it's only an idea how to make it and how to implement the libraries to understand Arduino code and to make it possible to program it, to develop software in Arduino environment. It's only about that. There are a lot of Arduino original boards. I said original because, as I said, there are not only Arduino from Arduino. Yeah, you can have Arduino, the boards made with Arduino philosophy, which are not from, which are not labeled with Arduino sign. But of course, there are also a lot of Arduino from Arduino. One of it is Arduino Uno, which we are going to work with here. And Arduino-like systems which work like Arduino, which are available in your Arduino development environment, which you can program, develop software for them in Arduino environment or not, but which are similar to this Arduino architecture. A few words about the GPIO. What the GPIO is, it's a general purpose input-output. It means that it's input or output, which the purpose is general. It means that you can use it for many various things. So you can realize in this in this example 19 pins, many different, many interesting devices, many interesting solutions. Solution would be the best explanation. Of course, that the general purpose inputs outputs are not assigned only to that. As you can see here, you've got here analog decimal converter inputs outputs from A0 to A5. But if we don't use analog digital converter, we can use these pins also like a general purpose inputs outputs. So for us as programmers, it's very useful and very comfortable to have such pins which we can use not only for some specific purpose, they are not sacrificed to do only one thing, but which we can use to many things which are dependent on the situation and on our idea. Okay. And in the end, some words about analog digital conversion. Well, I think that you are mostly in this topic, yeah, because as physicians, you have to know something, you have to be in this topic, so I don't want to teach you here. I'd like to only show you how I'm talking to my students, and maybe it will be some idea for you, because, well, frankly speaking, it's the idea of this course, yeah, that we are providing some sample lectures for you, which you are going to provide to your students then. Yeah? It's not an idea to teach you here, by us, yeah, but the idea is to show you some way how we are doing that, and maybe some parts of that would be available for you. That's why I decided to put it here about this analog decimal conversion, because I like explaining that this way, and maybe it will be interesting also for you and for your students. So, we know that we can divide analog decimal conversion in steps, in some phases, and the first of that steps is sampling, where the sampling is taking the value of real signal in the specific time. So when we have an analog signal, we can take every part of that signal and save it somewhere. And the question is, what are these moments? When are we taking this signal and when are we saving it? Of course, again, it depends. It depends on our architecture of our system and on the hardware and software which we implemented. And the parameter in the analog decimal converter is the sampling time, or on the other hand, it's sampling rate. So the higher the sampling time is, the lower the sampling rate is. So the sample rate, if the sample rate is higher, the quicker and the more often we are taking our samples. And of course, what's the main rule here? That the sample time of our system has to be at least twice as the period of our analog signal. Another step in analog decimal conversion is quantization, and in this step we have to decide what resolution we want to achieve in our result. And the parameter which describes it is exactly the same name. It's resolution, yeah? And resolution is explained in bits. Why? Because the result of analog decimal conversion is a number. It's a binary number, and binary number is written in bits. So if we want to have a binary number in the end, the binary number for sure have a digits which are bits. So the more bits in the number we have, the longer number we have, and the bigger part of information we can save in it. So, for example, we've got only if we've got only 8 states from 0 to 7, we can say that we can store this information in 3 bits, because in 3 bits we can save numbers from 0 to 7, which means that we can save 8 different numbers. Yeah, the bigger the number, the longer the number in the result is, the bigger the resolution of the analog decimal conversion is. And that way, the higher resolution of all the analog decimal conversion and converter is. So what's the main idea of quantization? After taking the probes, the samples are the black dots here in our schemes. Black dots are the samples. We have to understand that after sampling stage, after this first stage, which was sampling, yeah, we don't have this blue line anymore. The blue line is not there because in the moments which we decided to take probes, and it was every distinct, yeah, every distinct we took one sample, and after this process we got only these black dots. There is no more this blue line. So we've got only black dots. And what can we do with these black dots in the next step? We can approximate it to one of the recognizable levels. And what are the recognizable levels? It depends on the resolution of our converter. So there's the loop. The higher resolution is, the more number we can recognize in this axis. So the more number we can describe in this axis. And then more precise our estimation, our approximation is here. So there is the shorter road between the sample and the nearest recognizable level of the converter. And this is the quantization. Then we are moving to coding. When we recognize the levels and when we put each probe to one of the recognizable level, we've got each probe on the level which we can recognize. That's why here is all the process again. So from analog signal to sampling, so taking samples, then quantization, then moving each sample to one of the recognizable levels. These are recognizable levels. So when we decided that our analog decimal converter is only 3 bits, so we've got only 8 recognizable levels. So each of probes has to be moved to one of these levels. And then coding is only reading the number which is alongside, it stays alongside this recognizable level. So if we decided that this probe fits this level, so this level has a description, and the description is 110, and it's our code. What's going on with this code? This code goes to the register, to the output register of analog digital converter. For how long? For the time of next conversion, because it goes there and it stays there, and it's every converter software developer who uses this analog digital converter, and the software developer can read it from this register as long as another sampling starts, another sample is taken, another quantization is done, yeah, and another code, and it's here, yeah, it's 101, goes to the output register, and then it stays there for the time of another sample. So for us as software developers, because I'm talking to you now as to software developers, because it's the first stage of our adventure with software developing for microcontrollers. So for us as software developers, important is that after starting analog decimal converter, we've got this value there all the time. And when we put some input to analog decimal, put some signal to analog decimal converter input, it's the task of analog decimal converter to convert this, and for us as software developers, the only information is that I can always take this value from the output register of analog digital converter. And that's all. What about Arduino analog digital converter? There are a few numbers about the converter which we are going to use. So a short definition what the resolution is. I just told you about it. And we've got this resolution changeable. We can change it. Why can we change the resolution? How do you think? What could be a reason to change resolution of analog decimal converter? Is there any reason to do that? How do you think? Maybe not about a bus, but about the number number of data to convert. Because the bigger number, the bigger, the more data to convert. So we can't convert such big numbers when it's not necessary. So we have to compare our requirements to the power of our system. It's not only about the power of microcontroller, but because it's the composition of power of the microcontroller and the frequency of our data processing. If you want to process data frequently, we have to lose some, we have to decide to get smaller numbers to convert, because we are not able to convert big numbers, big data very frequently. Okay, some words about voltage which can be put into our analog decimal converted input, and maximum sample rate which we can use. And again, we can decide which sample rate we use, and the reason is similar. The more data, maybe the bigger sample rate, the more data. The more data are coming to us, if we want to read it, because the analog digital converter can work with, for example, 10 kilohertz, and we cannot use it in our processing. But if we want to, it's a huge amount of data in our process, and it's not always required in our system. So we have to decide which solution is the best for us, and almost every microcontroller allows us to do such thing. Okay, and the last sum up about conversion. So we've got this analog signal sampled in described moments, and then converted to the decimal, to the binary code. And thank you for your attention. No, I think that Chris is delivering some
yes,
presentation.
The last presentation. It will be not so long. No worries. Zobacz, jak zaczynasz ludzi. Bardzo dobrze. Okay.
Fortunately, it was the only theoretical lecture about programming. More about it in practical ways. It's much easier.
No, zaraz koniec. Września. Próbuję dzisiaj jeszcze jednak. Jeździcie też jest takim rzęsem? Też robicie tak na ostatnią chwilę, co? Nie no, 15 slajdów. No jak nie piszę, to znaczy, że się jadę. Gdzieś tam jest. Nie interesuje. No, akurat no, do kolei. Sangre, później jakaś drzemka, sangre,
Tak chodzi, że to jest sangry.
no właśnie, inne, no. Może oni inaczej to nazywają. Pewnie jakiś serwerek, nie? No. No ale jest, pewnie też rzucamy, nie? Ale z tej prezentacji zrobię publikację. Tak. Prawie. Nie ma nigdzie, kurwa, wszystko. Ja chociaż znalazłem, to łatwo poszło, ale nigdzie nie znalazłem. Sam sobie. Jeszcze co piszą o safety w kontekście, wiesz, bezpiecznego latania, przestrzeń, wiesz, takie rzeczy. A nie... Pytanie, ale nie.
Ale za parę lat.
No, może, a my będziemy latać do innych krajów też to robić, czy już nie? Prezentacje?
Na Malajii też wrócimy.
Nie, ale tam jest ta armia.
Potem na Kamar.
Dobra.
Nie wiem. Nie wiem.
13? Czuć, tak 26.
Да, я уже знаю.
After we start, it finishes. So today in the last presentation we will talk about road safety systems. So the prevention of safety during your flights is one of the most important issues. In addition to the level of regulations and suggested behaviors, there are devices and programming solutions that are meant to facilitate this task. So on the next slides I will try to introduce them to you. I'm not going to talk about any regulations and stuff like that, but I will try to show you what are actually the hardware and software ways to make that flight really be safer, more safe. Okay? So, as you can see from the general objectives that we drawn, I would like to put the general effort on the hardware side. So the next chapters, the presentation will be as follows: safety light, redundant systems, safety algorithm, light illumination system, parachutes, airbag, parameter control, and other one example that I will show at the end. So starting from the very beginning, the first element that could be connected to safety are the lights. So as with large aircraft, lights are necessary for operating in the airspace. So the solutions used in the UAV are also taken from the communication edition. Some solutions involve the construction of an aircraft. Others will be used on airplanes, others on helicopters. So, for example, with the navigation and position lights shown on the left side, our lights designed to be easy to install. They must remain durable, lightweight. So this is the most important thing. These units are normally wing tip mounted. So the lens protects the LED optics, which is inside, and provides 180% viewing engine. So the lights allow for the navigation, because they are red and green, and the collision strobe to be operated independently. The other lights, landing lights, normally these LEDs are mounted to a specially designed base plate that acts as a heatsink to ensure non-light operation. This unit also should have a wide angle to light for maximum visibility. The last lights are the beacon lights that provides a 360 degrees red strobe, or very high intensity aviation red. With 625 millimeters. So the beacon light can be found with a simple faded flash pattern of approximately 1 Hz. And the last lights are the anti-collision strobe that provides a 600 lumen flash of light, also at approximately 1 Hz. And it can be viewed for 230 degrees of the wheel of the aircraft. So those who work with drones are always aware of that not all activities can be carried out during the daylight hours. So on the contrary, there are some activities that are specifically required to be done by night, because of safety or, for example, technical reasons. So lighting systems made specifically for the type of this activity are going to play a fundamental role. So, as an example, according to FAA regulation, the Part 107 rules, you can fly your drone during the day. So, and the daylight is from 30 minutes before official sunrise to 30 minutes after official sunset. That if you are flying during that 30 minutes CUT light period, you need to have light radar visible for at least 3 miles. The regulation from FAA. So if you are flying in that time, you need to put some safety lights that are shown, for example, here. There are 2 different solutions, especially for multi-locals. The left are DJI anti-collision lights, and the right is the most popular solution that can be found in the market. The next important thing in safety is redundancy. So in many safety critical systems, such as, for example, fly-by-wire or ground systems in aircraft, some parts of the control system may be, for example, triplicated, which is formally termed as the triple modular redundancy. So an error in one component may then be outvoted by the other 2. So in a triple redundant system, the system has 3 sub-components. All 3 of them must fail before the whole system fails. Since each temporarily fails and the sub-components are expected to fail independently, the probability of all 3 failing is calculated to be extraordinarily small. So as an example, in case of this Airbus aircraft, besides the 3-mine flight control systems, 2 backup systems are available to help isolate the faulty one. So inside each has 2 channels which run software written by a different team or run on processor different to the one in the other channel, and which are supplied by 2 different suppliers. So this solution helps to reduce systematic error when altogether would fail because of the common malfunction. So this is an Airbus flight control system diagram. Only the first system of which is expanded. So the boxes for system 2 and 3 look the same. Inside, input is from the side sticks and output goes to the hydraulic belts of the control surface. So the coding happens first in the temperature step between the 2 channels and again in the filter between the single systems. So the UAVs can be the redundancy in different levels, starting, for example, from batteries and the other elements. But the most important thing, which is autopilot, can be also redundant. So redundant autopilot are often composed by 2 or 3 equal autopilot modules, all managed by an article. So these modules include logistics for monitoring the operational status of the electronic component. And in the case of failure, in one of the autopilot flight control, changes to another module. So at the same time, the system notifies the operator and executes, for example, scheduled fail-safe or fail operating process. So all this must be executed in a split of seconds, because in case of an error in extended time, just a few seconds could be fatal for the device. And also the common use of servos in unmanned aircraft usually is the management control surfaces and in failures. So redundant servos have also 2 redundant input buses in order to give them higher reliability. So due to the stage redundancy, it's possible to avoid critical failures in UAV if one of the internal buses of the control system fails, or if the wiring between the control systems and the servo is not the one performing the expected task. So we would have a second line of range to maintain the navigation with no incident. We can also look on the redundancy from different levels. So when it comes to safety, one key is consideration of propulsion redundancy. However, not all drones are made equal, and it is important for operators to understand the key difference between drone motor configuration and the specific behavior of each configuration will control failure. And so the propeller is attached to a motor which spins either anti-clockwise or clockwise. So this creates thrust, but also a clockwise or anti-clockwise moment. So in simple terms, the moment is a measure of its tendency to cause the body to rotate about a specific point or axis. So the moment created by will be in the opposite direction of the propeller spin direction. So this moment is not cancelled because the drone to spin. So if the thrust is too much on one side of the drone, it will cause the drone to flip to the other side. Hence, thrust must be balanced on all sides for stability. And building multi-rotors, we have to take this problem and solve it at the very beginning. Because, for example, in quadrocopter, which is the most popular configuration, quadrocopters have 4 motors, usually arranged in the X configuration. So quadrocopters may still be controllable when one side of propeller breaks, but when one motor fails, the quadrocopter will flip on the top. So the other solution is hexacopter. This is also very popular design, and it is really used when the drone needs to use a pivotal load. So N2 motor spins clockwise, which generates anti-clockwise moment. And when N2 fails, there is a loss of anti-clockwise moment because it's a net clockwise moment. So to make matters worse, while M1 and M3 spin faster to compensate for the lost thrust, we create more clockwise moment. So the platform has the net clockwise moment and it will start spinning in the clockwise direction. But in modern drones, in intelligent course alert feature, the drone will still be controllable by a moderately skilled pilot, since the computer on board will take pilot input command and transform it into actual commands relative to the drone head. And the last solution is octocopter. This is the most expensive design, but this configuration is less efficient in propulsion. This is because for an equivalent size quadrocopter will have more space between motors to spin longer propeller. And of course, in this kind of multicopter, one of the motors will fail. There is the control system will make that there will be no more net moments and the drone will not spin. So in conclusion, the octocopter design presents the best chance of recovery when one motor fails. The next safety systems could be phase. Phase is a special stage where the drone is considered as without control. So the control clock between the radio and receiver, radio to and off. So it is a set of instructions that the flight controller will execute in case close interface is failed. So, for example, in case of loss of GPS signal, the UAV should attempt to reconnect. UAV will hover for established time. Once the established time has expired, the UAV will, for example, land on south. If connection is reestablished, the UAV should immediately return to launch or evaluation. So ground control signal. So the phaser activates when remote signal is lost for more than 5 seconds. It depends on the kind of UAV. But the default setting is to ascend to a preset altitude and have the routing for the home point. Another option is to have the drone go into hover mode until it either requires the signal on or runs out of the battery and perform automatically. The third option is to set it to land wherever it is as soon as it loses signal. In the third scenario, low battery, this is triggered when the intelligent battery drains to a level that may cause problem in returning of aircraft. So when the battery level reaches the minimum level required for the aircraft to return to home, phaser system will be activated and the aircraft will automatically go home. If the controller determines that it's not enough power left to get the drone all the way back to the home, it will automatically land the drone rather than have it just fall out of the sky. The other option is flight termination system. This device actually the future device looks like a small box, but it allows you a simple button to terminate all operations and function of the drone. So in short, a real soft power that comes through our eye and the remote control unit respond. So thanks to that flight termination system, the drone stops working failed within the area of operation, already previously put on a safety guide operation, thus avoiding the remote control failure, causing the exit from the control area and the filter viewing, causing images of personal injury. So it immediately terminates the flight and therefore becomes open. So the only solution that you can minimize damage with the drone after the impact is with a parachute. So actually there are three main types of parachute. There are parachutes that are very cheap and easy to install. They are installed on the up of the UAV. There are also parachutes that are inside the car, and it could be the opening process could be very slow until it needs a high altitude to perform this landing by the parachute. And there are also parachutes that work with CO2 trigger system, and they don't need so much height like the others. And I can show you some examples. This is the example of the safer pyrotechnic parachute recovery solution. It clips on the top of the drone. So here. And it automatically deploys when free fall is detected by bolting chip. So actually, this producer offered the reusable module, which is called SafeAir, and it is suggested for the compact units for drones weighing 2 kilograms, and also for larger ships. Normal users of this system can customize the speed of the drop rate. This is between the 3 to 6 meters per second. And it can be also activated at the low altitude. So it looks like the perfect solution to use, especially in the urban area. The other solution is Skycap. It is the smallest and the lightest parachute system on the market. It's starting at just 115 grams. Including the parachute. And Skycap ejects the parachute like a bullet for beyond proper spinning radius. So in a fraction of a second. And what is important, rearming the launch mechanism is possible without any special tools, and it takes only a few minutes to repack it and prepare for the normal launch. And the producer says that it can be installed on almost any aircraft from 1 to 23 kilograms. And the multiple parachute sizes are available, and also up to 3 units can be installed on one unit. So for the large UAVs, there are different ways of using the parachute. So in particular, it depends on the UAV design. So for example, Predator UAV has a normally partial prop, so requires the use of forward deployment method to ensure that the parachute will clear the prop. So there is a tractor rocket system that was selected for a crossing deployment of the main parachute. The next solution that actually was shown last year at the beginner, but we are also working on it in Poland. So this is an airbag for drone. This airbag, like a parachute, can be deployed by a pilot based on activation signals, or by the or it can be automatically deployed, detecting the condition warrant activation. So such conditions include, for example, power failure, motor failure, guidance system failure, unexpected change in control source, and to others. So the airbag is inflated to cover the hard, sharp, and spinning parts of the drone, for example, propellers and the frame. And as a result, any part of the drone is with the airbag rather than a hard or spinning component. So all the previously mentioned components, in order to be activated, must have final information about the actual state of the UAV. So it can be done by the standard UAV controller, but it may not work out in case of their failure. So there is another autonomous solution based on an independent module for monitoring UAV parameters. And for example, this is a parallel computer designed specially to work with flight elimination and parachute system. A smart emergency computer for autonomous recovery today, which monitors the drone systems and flight pattern to deploy safety measures as necessary, including in cases of loss of control, free fall, power outage, and other critical malfunctions. There are also solutions more sophisticated. It is possible to have, for example, elements with built-in monitoring functions. So, for example, there are servers that have information about its current position engine in comparison to its origin. And there have also electronic sensors that can provide information about exceeding critical values, and especially designed architecture to work out redundancy. And at the end, I'd like to present you some new idea to increase the security of UAV. So it is also the solution from the last year. The company Teomatics received a patent in the US for innovative alternative to known safety system such as parachute system. And this is done by the construction of at least 2 classic lift elements are arranged radial symmetrically about the jaw axis of the jaw. And in the case of 5, these twisted passive lift elements initiate the rotation about the heel, whereby the position of the drone will be stabilized in the space. So furthermore, the rotation generates a dynamic lift which reduces the fire and crash velocity of the drone. So, in conclusion, we can say that the safety systems are just important as for a large organization. The solutions will be are similar like in the communication aviation, but there are technical issues that are connected with the limitation of mass, dimensions, and for example, energy needs. And if we are going to see what will happen further, we are talking about use case, about flying in the urban area, you can see that there is a strong need to develop safety systems that can have appropriate level of safety when the wave is working above the heads of the people. So I think that's our communication side. Thank you.
Okay, do you know the schedule for this week or not? Have you seen it? So maybe shortly I will show you my book.
The top is safe?
Okay.
Yeah, I'm sure it can be.
Sorry, I have one question. Do you send for us this presentation?
The presentations are to be published in this e-learning portal. Yeah?
Okay.
So all the presentations from all the course will be there. So it's for today. Okay, mine are yellow, but it's it was just passed, yeah, the Thursday. Tomorrow, again, lectures, 8 hours, delivered by other people, but also lectures about batteries, regulators, and power systems, generally speaking. Then from 3 is about PCAS, ADSB, so sensing the void, yeah, generally speaking. Then some information about navigation systems on board and another about navigation systems. Okay, and it will be the hardest for you because it's another day with lectures only. But on Wednesday, we're starting with one lecture about radio recordings, and then we are moving to practical classes. First about Audible radio, then about autopilots, and we'll try to prepare something with your autopilot, yeah, because if you bought it, it's already here, it's good to know something about this one and about something another. And then my part about programming, so we'll have some fun with Arduino. And it's all about Arduino, peripherals for Arduino. And then another lecture in the afternoon about various equipment like sensors, gyroscope, and so on. And then again for Arduino and peripheral, it's another device for Arduino. It's Thursday. It's Friday. It was Thursday, and now on Friday we're starting with workshops about Arduino, and then lectures about control systems. Another lecture from me about ground control station, but there'll be much less theory, much more about practical solutions. And in the end, equations of motion, so it will be really good information at the end. And that's all. If you want to share it with you, I can pass it. Because I think that it's not available online anywhere, this topic. Or am I wrong? Did you have it in some email? Or? So if you want to know what is going to be next game, share it. Okay, that's all for today. See you tomorrow. Good night. Tomorrow. We'll know it after today, because we'll try to do something with this one, yeah? But if we can't start then the Arduino classes are on Wednesday, so we have tomorrow to decide. Okay? Because if we tell you tomorrow, it's okay for you.
Udało się dośpieć.
Ja się sugeruję. Nie, ja się
Ja też
no tak.
No, aha. Dzisiaj do końca miał kupować tego. A coś nie ma. A nawet dopiero 14 no tak.
Да. Сейчас, да, это же Слава работает с Евгением, который работает.
Какое слово?
Сейчас спрошу, даже не знаю, потому что это работает с профессором Евгением, который работает с
To by się wyłączyło.
Is it okay? I was in. I mean, with this electrical parts.
Nothing separate.
Okay. I will do it. Don't care.
Dziękuję. Czy raz wody?
znajduje, to nie wasza praca. Były proste
Потому что нужно изучить этого человека, чтобы он был. Человек, который будет и в ответе,
To ciekawy temat. W Armenii nie można kupić tych układów. Хорошо? Все, спасибо. Teraz coś w ogóle nie. Nie, to już jednak no to się zawsze pierdolę. Aleksandr już coś tam zainstalował. Czas szybko. No.
Tak, no, że tam... No, to jest napisane, nie? To jest ładnie
Kupili ramy, kupili regulatory, a wszystko i składali zupełnie tymi kartami. To nie ja. No. Tak. Ja pewnie tego ćwiczenia był w piątce zaczęło lat. Nowy kontroler dla programu. O której?
No nie wiadomo, ostatni średnio widziany 12:32. Nie wiem, którego czasu, szczerze mówiąc.
No to też jest powód. Trzeba się prześciło światło, że tam no na telefonach jest naszerzenie, że tam dopiero jest 14. Nie, no to ona chciała się od razu przełączyła. To masz automatycznie. No 15 tutaj. Na to, że jest.
To co?
poate e număr de dată.
Вчера не было ответственно, да, что каждый раз надо написать. Знаешь, что сейчас помоглись,
Да.
было каждый раз надо пожалуйста.
Да, я после курс.
И нам сказал, вот, парень, что чтобы вообще вот эти штучки, видишь, вот эти,
Да, вижу, вижу, да.
повернуться туда.
Это точно будет большой мир, я пробую.
Но зубы, ну хорошо, может туда. Нет.
Я поэтому, что вот туда направишь, потом, чтобы... Так, что угол ограничен, ты можешь понимать? Но будет, да.
Знаешь, когда сидишь, чуть-чуть,
Я почему говорю, что я думаю, что можно
Пусть тебе.
заслон,
Так.
чтобы она
Вот эти
как-то ограничена.
дверь для наших спектров, да?
это ночные ворота, да?
С 6 до 58. И вот уже идет процесс.
Смотри, я
После этого уже надо будет создавать второй диск, потому что мы зайдем, и у нас покажет только один диск, на который мы еще ставим всю систему. А второго диска он не будет. Потом мы его создадим.
Нет, понятно, что это дело, но как, естественно, запомнишь это.
У меня еще 5 экзаменов.
всего лишь.
Сегодня. Еще завтра, на завтра вы успеете поставить вот эти 4. И я так ноутбук, если не успею возить с собой домой, ставить
А
систему.
может завтра будешь спать ночью?
С утра? Я боюсь, что с утра не успею.
Он нужен будет в среду.
Подайте ее в среду.
Он нужен в среду.
Завтра. Завтра будет еще теория.
Да.
А можно вот так сделать? Давайте поставим все компьютера.
Все сюда, все четыре.
Все. Один здесь. Вот. Еще одну.
Записываешь, да?
Да, записываем. Еще одну. Давайте, если я... Курнем,
Да.
давай, если я забываю.